All right. It's great to be here, and thanks Graham for organizing this event, and for the Weber School. This has been really fun. And as Graham said, I run the EPIC lab at Georgia Tech, and I'm excited to talk to you today about my research program where we are merging AI and human physiology for natural and intuitive control of wearable robotic systems. Mobility deficits impact a wide range of individuals, such as individuals who've had stroke, or children with cerebral palsy, or individuals with leg amputations. Mobility issues are among the most prevalent deficits in older adults in the United States. Lack of mobility increases cost and burden on society and reduces independence and health, which leads to a lower quality of life and prevent participation in important life activities. Solutions that can meaningfully address and improve mobility could be a huge benefit for society. A key question is whether emerging robotic technology can restore or even augment human locomotion performance. And new and promising wearable robotics are coming onto the market, like those that you see here, and we really want them to be able to improve older adult mobility, increase safety for workers in industrial jobs, and restore movement to individuals with limb amputations. So why don't we see these robots ubiquitously in society today? The reality is that real-world human movement is messy, it's variable, it's non-cyclic, and it's a huge challenge for the control systems of these devices to handle this level of task diversity. And our new challenge in the field is how do we ensure reliable control of these devices across in real-world environments that require this kind of high level of task diversity. So our early research to try to tackle this problem focused on the idea of activity mode classification. Basically, one could take the sensors from within a robotic device like this, like the prosthesis that you see in this video, input it into a machine learning classifier, and output discrete activity modes such as level walking, going upstairs, or going down ramps. And with this system, the amputee just needs to think about kind of going up those stairs or down the ramps or doing sit to stand, and the device transitions quite naturally between these modes thanks to the AI. So we thought this could be a great solution and a really promising strategy for handling real-world task diversity. But what happens if the classifier makes a mistake? What if it's wrong? So one issue with classifying the world as a whole bunch of discrete action states is that if it chooses the wrong state, like it doesn't transition properly or triggers into a stair mode accidentally, it could lead to a fall, which is really the last thing that we want these devices to do. Compounding on this, real-world human movement is substantially more variable than just a few tasks like walking and stairs. It also consists of many non-cyclic, transitory motions that are not well described by singular tasks and may have overlapping characteristics with each other. Creating discrete activity classifiers to handle all types of human movement is relatively intractable, and there may be dozens of different discrete tasks that we need to handle. So the key question that our lab has been focusing on is how do we develop systems that can handle a great variety of tasks that include both cyclic locomotion as well as these transitory, non-cyclic kind of tasks. And in addition, we want these systems to work well across a wide range of human users with various pathologies, which you can imagine is quite the challenge. So, as many others have, we turn to AI, and in particular, deep learning is a powerful tool that has been emerged to solve highly complex problems like this. We've invested heavily over the last 10 years in curating really huge data sets of human behavior that can go into training these kinds of systems. And the basic idea is that we could fuse sensor information inside a wearable robot with deep learning to estimate the human's intent. However, instead of leveraging AI to estimate external states, such as activity classifiers that estimate things like level walking, stairs, and ramps, our breakthrough really came when we completely reimagined what the AI could do. So rather than trying to estimate everything in the human's environment, our idea was to estimate what's going on inside the human, or the physiological states of the human, and wrap our wearable robotic controller around the internal mechanics of the human for a unified approach, or as we like to call it, task-agnostic control. So let's go into this. So when humans walk, they generate a biomechanical state called a joint moment. These are effectively the torques produced by your muscles around a given joint in your body and can be used then to inform a relatively simple unified control policy, mapping kind of these internal joint states like the joint moment of a knee to robot joint torques. And so there are really two strategies we could get at to get these internal states. The first is we could measure these directly through invasive means, such as through surgically implanting sensors in the joints or muscles, but this may not be very palatable to many people who might want to wear a robot like this. Instead, we can use a combination of external sensors that we place on the human and combine this with AI to reasonably infer these internal joint states. Okay, so now let's introduce our robot today, which is an example of a system that has taken this second approach. Okay, here's Ethan today as our pilot to show off this device, which we call the Hike exoskeleton or HipKnee Exo. When many people think of an exoskeleton, they think of a large, bulky device with rigid metal struts going outside the user, which was certainly true of these devices last decade. This is a vision of a new class of wearable robotic systems. The next generation of wearable robotics will be integrated into clothing, lightweight, and sleek. This device is a pants-integrated robot that provides assistance bilaterally at the hips and the knee joints, and is capable of replacing about 20 to 25% of the work done by those joints. And the idea in the future is it would be as simple as just putting on a pair of pants to don one of these systems. And notice that the system doesn't have any orthotic cuffs. Right? So instead, the force is transmitted through the pants, which is stretchy and comfortable in key locations, but it's tight and compact in others to allow forces to be transmitted comfortably to the human user. The system is also highly agile with a number of different degrees of freedom. An example of this is it has a really cool translational joint that basically changes the distance between the hip and the knee, which allows the actuators to stay aligned with the human joints during movement, which is really critical. This freedom of movement allows the system to handle a great deal of different recreational and occupational kinds of tasks to be accomplished in the system, which was really a main key feature of the design. And then also, this system has a large sensor suite built in. So this includes IMUs on every segment of the lower limb from the pelvis to the foot, encoders in each joint, as well as force-sensitive insoles in the feet, which allows it to measure ground reaction forces. This detailed sensor suite gives the AI a plethora of rich information to determine the relationships between how the human is moving in it and the underlying physiological state of the user. So how do we leverage all of this sensor data to estimate these internal states? So basically, what we do is we take them inside a big biomechanics lab at Georgia Tech, put them in a motion capture suit, similar to what you would see in an animation studio, have them walk on specialized plates in the floor that measure their contact forces with the ground. This allows us to use a powerful musculoskeletal modeling software, which you see pictured here, called OpenSim, to determine the internal joint biomechanics of the human, which serves then as the ground truth training examples for the AI to learn the relationship between the wearable sensors on the user and their ground truth internal joint states, joint moments. And our unique approach was collecting this data matched. So we basically take the exoskeleton, somebody who's wearing it, put them in the big biomechanics lab, and have many different people perform lots and lots and lots of different tasks. And so our system now includes over 50 subjects, each performing over 60 different kinds of activities. And this included standard cyclic activities like walking stairs and ramps, but also non-standard cyclic activities like tire running and skipping, walking backwards and shuffling. And even more importantly, we collected a wide range of non-cyclic kind of tasks like navigating curbs, lunging, jumping, lifting weights, and even tug of war. The idea was to try to collect a highly diverse range of different movement that encompasses most of the things that you would normally do with your lower limbs during recreational and occupational tasks. Thanks, Ethan, for the demo. Okay, so once we have all this data, we can then basically start putting it into an AI system. So basically it takes all the exoskeleton sensor data, estimates the internal states of the user through this deep learning, and then we deploy these very fast on AI systems through what's called an NVIDIA Jetson Nano, which is basically a microprocessor that allows these instantaneous joint moment states to be computed every 5 milliseconds, or 200 times a second for fast, smooth motion assistance. The system really doesn't have any idea what task you're performing. It's just estimating the internal efforts of your joints, which allows for this kind of task-agnostic control. So let's take a look at then assessing the system. Here we have a circuit of activities being performed by this exoskeleton user. In the lower graphs, you can see the instantaneous outputs of the hip on top and the knee on the bottom. The black line shows the AI estimate of the internal joint moments, while the red line shows the ground truth, which is only available when he's stepping on a force plate in the lab. And as long as these two match well, there will be excellent synchrony between the exoskeleton and the human user. Notice that we have natural and smooth transitions across all of these different kinds of tasks, just like human movement would be without any kinds of discontinuities. And then we can assess this formally through a metric that we call the correlation coefficient, which basically tells us how closely these estimates correspond to the ground truth, and we can look at this across lots of different tasks. 100% here would be a perfect synchrony between the exoskeleton and the user. And while this varies depending on the task, we generally see this correlation to be on average over 90% across tasks and joints. This is more than sufficient to maintain excellent synchrony between the exoskeleton and human user. Now I'm just saying that, but how do we kind of prove this? Let's look at are we able to augment human capability and performance? And so the standard for this, the gold standard for this measure is something called energetic cost. And in the field, this is measured basically by putting a breath mask on you and taking in your oxygen intake, which calculates then how much energy you're expending to perform a task. And what is exciting that we found, the system not only accounts for its own mass that you're wearing, but it can significantly augment humans by a further 5 to 15% depending on the task, which in these tests is compared to not wearing any device at all. And for reference, those level of improvements is the equivalent of offsetting the added mass of a 10 to 30 pound backpack. So that makes it significantly easier to move, and this is a big leap forward in terms of meaningful human augmentation beyond normal human capability across a range of different tasks. Now, another measure we might care about is human safety, right? So the gold standard measure for safety is something called a joint load. This is basically the bone-on-bone contact loading in your joint. And in this study, we focus specifically on the knee joint loading because that's a joint that's commonly injured in occupational tasks. And so in this study, we assessed 13 different occupational tasks for joint loading, such as those that you see pictured here, and found reductions relative to not wearing any device in 12 of the 13 tasks, which is quite promising for worker safety. Okay, so it's really great that we can augment able-bodied young adults, but for this last part of the talk, let's discuss how we can translate these approaches to clinical populations, such as individuals who've had a stroke. So stroke gait is highly non-uniform in that they typically present with lots of different kinds of walking styles, often with an asymmetric gait and quite varying levels of mobility impairment. And so the key challenge is how do we adapt our approach to handle real clinical gait? The issue here is that an AI model trained purely on able-bodied individuals is not going to work. So, similar to before, we need lots of data, in this case now from real stroke users, with representation across the mobility spectrum, as well as their full biomechanics of motion for training these kinds of AIs. And so for curating this training data set, we surveyed our patients and clinicians about what kinds of tasks they would want an exoskeleton to help them with, and a wide range of functional activities of daily living emerged, which we tried our best to simulate in the lab, as you can see here. And now we have data from 25 different patients across 39 different activities of daily living that include things like getting in and out of a car, doing Tai Chi, stepping over an obstacle, pushing a grocery cart, and many others. So once we have all this data, we can then train large-scale AI models to understand the specific internal physiological states of individuals with stroke. For this clinical trial, we use this hip exoskeleton, and similar to before, we take in exoskeleton sensor data into a large deep learning network and output stroke-specific joint moments. And we can see this in the bottom right. This is, again, the AI accuracies. On the top here, we're looking at the paretic hip, which tends to be their more affected side. On the bottom is their non-paretic hip, which is their less affected side. And in general, we can still see excellent synchrony between the exoskeleton and the user, even on the paretic hip, which is substantially harder to estimate because it's far more variable across different users. And this was also observed across a wide variety of tasks like those seen here, so beyond just walking. You'll notice that we still have an average of 85% correlation between the AI system and the underlying ground truth, which is still excellent to maintain a task-agnostic controller for individuals with stroke. The next question in the clinical trial was, could we improve biomechanical outcomes in stroke gait? An interesting characteristic of stroke gait is they shift much of the burden of their walking from their ankles to their hips with a very hip-dominated form of walking and end up with heavily overtaxed hip musculature. Our hip exoskeleton was able to relieve the hip energetic work by 15 to nearly 25% across different modes, which is quite promising. And then what I also think is really cool is how this translated into some very nice clinical outcomes, meaningful clinical outcomes for our patients. Sit to stand, as you see here, was one of the most impactful maneuvers that patients thought the exoskeleton was extremely useful for. Here you can see how difficult it was for this patient to get out of this chair without needing kind of extra support. But as soon as we turn on the exoskeleton, the patient's able to get out of the chair without any type of external support. We also looked at whether the exoskeleton can augment both speed and endurance, and we saw nearly a 10% increase in endurance and a 7% increase in achievable maximum walking speed compared to not using any device. And these are very impactful mobility gains for patients, so we were very excited about this kind of technology. Okay, to wrap up, I think the future of wearable robotics is very bright. The next generation of wearable robotics will be clothing integrated, AI-infused systems that are synced to the underlying human physiology of the user and can support both clinical conditions, recreational activities in older adults, and occupational workers. I hope everyone will look forward to a promising future of ubiquitous wearable robotics in society. And lastly, I'd like to acknowledge the many students and collaborators who made this research possible. It's a huge team's worth of effort over many years, and also a special shout out to our funding sources, and in particular NSF and NIH. All of this kind of work grinds to a halt without these very important funding agencies. Thank you for listening.